All right, so a long time ago, a guy named Rene Descartes. He did it's kind of a Renaissance man. He did a lot of things. He was dabbled in music, philosophy. If you ever take a philosophy course and hear the phrase, I think, therefore I am, that's Rene Descartes. But he also dabbled in mathematics. You can thank him for things like this. The old XY plane or the rectangular coordinate plane. He's the one who originated that. It's actually officially called the Cartesian coordinate plane. So he was thinking about this. Square root of -1. All right. So there is no real number that you can multiply with itself and get a negative number, let alone specifically just -1. So he decided, call it something. I can't call it a real number. So he called it I. And officially we call that the imaginary unit. So it's not a variable, it is a number. And once we make this assumption, if we would square both sides of this equation, of course, you square root, you're going to get what's inside. So you're just going to have -1 there. And of course, you square I, you're going to have I squared. So I squared is officially the number -1. So that allows us now to talk about just simplifying square roots, such as if I had the square root of -9. So before we would just say, okay, that's not a real number. But now, since that is -1 and I can take roots of individual factors, the negative will come out as a root of I. And then, of course, the square root of 9 is 3. So this is now 3i. If you would do something like, say, the square root of -8, then again, the square root of a negative is always going to be extracted out as a root of I. And then 8 is not a perfect square, but it has a perfect square factor. And we would say a radical is not completely simplified until all nth root factors have been extracted. So 8 is 4 times 2. Square root of 4 is 2. So it would officially break down 2i square root of 2. We good with that? Now, always don't overextend. Be careful. What's that?
Would it be 2i?
No. Oh, no. So what's the difference on this one? It's not a square root. This is a what? Didn't mean to put that in there. The root is what?
Cube.
3. So it's a cube root. So we're looking for a number to multiply with itself 3 times and get what's in the radicand. That is underneath this, the radical. And so the deal here is, go back to the original definition from Descartes. It was defined as a square root of -1, right? Not a cube root. So the deal is any odd root, if you take a cube root, 5th root, 7th root, 9th root of a negative number, you will get a real number. You will not get I. And in this case, what number multiplied with itself 3 times is -8? -2. -2 times -2 times -2 is -8. So only extract out that I when you're looking at a square root of a negative number. Right. Okay, so this section 1.3 is all about the set of what we call complex numbers, and we actually have not defined that yet. Another guy later who actually became, again, he lived a long time ago as well, but he became known as the world's greatest mathematician that ever lived. And his name was Friedrich Karl Gauss, G-A-U-S-S. And Gauss actually constructed an entire set of numbers. And this is probably going to ring some bells. A plus BI. And again, this is going to be referred to as a complex number. Okay, so in this, A and B, and I'm going to throw some math notation at you. Are you familiar with set notation? That little kind of strange looking E here means element of, means it's going to belong to a set. It's going to be an element of the set of real numbers. So A and B are real numbers. This part, the A, that doesn't have the imaginary unit, it is referred to as the real component. And this is known, the part that has the imaginary unit is known as the complex component. Notice if B is 0, then this whole term is gone and you're just left with a real number. So the set of real numbers are a subset or part of the set of complex numbers. So any real number is also a complex number. Now, in actuality, and one of the most unfortunate namings of naming things, you know, calling I imaginary number, that imaginary unit, it sounds like make-believe. And I presume it kind of got the name imaginary because it's opposed to real. However, it is a number, and it is not something that is just, you know, out there in some sort of esoteric thing that we're just studying, but it has no real impact. It has an enormous impact on our everyday lives. We measure resistance on an electrical circuit, and all kinds of other things about electronics are measured in complex numbers. So when we talk about just these things we love to hold, or good old phones, electronics, all kinds of engineering are measured, engineering things are measured in complex numbers. So they're very practical. Now, if these are numbers, we should be able to add, subtract, multiply, and or divide them and get another complex number by those 4 operations. So kind of quickly looking at that, what I'm going to do is simply, by concrete example, talk about how to add, subtract, multiply, divide complex numbers. So if just randomly picking, say -3 plus 2i, and I'm going to add that to the complex number 5 minus 4i. Now, technically, you know, it's not in A plus BI form, but subtraction is defined as addition of the opposite. I could write this as 5 plus a -4i. It's just easier to write it as subtraction. Anyway, the hope would be, if you were going to add 2 complex numbers, it would just be like combining like terms. And that's exactly how it works. I would take the real components, -3 plus 5, I would get 2. And then 2i minus 4i would be a net of -2i. And so that would be the sum of those 2 complex numbers. Subtraction would work much the same. And I'm just going to take the same 2 numbers, -3 plus 2i, but this time subtract 5 minus 4i. So the one thing algebraically to remember here, you're going to have to distribute the negative first. So -3 plus 2i minus 5 plus 4i. And so I would have -3 minus 5, which would be a net of -8. And positive 2i plus 4i would be plus 6i. So subtraction is fairly straightforward. All right, let's go over this, make a block here. And let's multiply. So if I had -3 plus 2i, and then multiplied 5 minus 4i, the algebraic process of multiplying is going to be like just multiplying polynomials. I would think of FOIL for your first outer and inner and last products. And I would have -3 times 5, which would be negative 15. Negative 3 times a negative 4i would be a positive 12i. 2i times 5 would be 10i. And then 2i times a negative 4i would be a negative 8i squared. And this is where I need to remember that I squared is negative 1. So then simplifying this, I would have negative 15. Adding these two up would be 22i. And then this would just be plus 8. Are we okay with that being just saying plus 8? Simply because I squared is negative 1 and negative times negative is positive. So finishing it off, I would have negative 15 plus 8, which would be a net of negative 7, plus 22i. So multiply two complex numbers, get a complex number. All right, so one last operation, that's division. So I'm going to turn the page. And turn back because I've already, just to remind myself, what were the two numbers? Negative 3 plus 2i and 5 minus 4i. See if I can remember that. Negative 3 plus 2i. And the other one was 4 minus 5i.
5 minus 4i.
Thank you. 5 minus 4i. Okay. All right, so this is division. It would be negative 3 plus 2i divided by 5 minus 4i. So the algebraic technique here is to employ what we call conjugates. Now, conjugates are simply this. If you have the sum of two terms, its conjugate is the difference of those same two terms. If you have the difference of two terms, its conjugate is the sum of the same two terms. And the reason I'm picking this is, this, if you just multiply it out, we call difference of squares. It multiplies to be the difference of squares. That is, you would get, a times a is a squared. But on the outer and inner products, on the outer, you're going to get a negative ABI. On the inner, you're going to get a positive ABI. So the outer and inner products are always going to add to 0 and be gone. And then you're going to get minus b squared I squared on the last product. And then I squared being negative 1 means this is ultimately a squared plus b squared. So when you first learn factoring in intermediate algebra, and you're told difference of squares factors, but sum of squares never factors. That's true only that it doesn't factor over the reals. Sum of squares does in fact factor over the complex numbers. But for our purposes of division, whatever the bottom is, multiply top and bottom here, so you're multiplying just by 1, and multiply it by its conjugate. And so that, in this case, it would be 5 plus 4i. So what that sets up, the bottom is really easy because we've just worked out for any two complex numbers here with a and b, whatever those real numbers may be, that it will always be a squared plus b squared. So the bottom here has to multiply to be 5 squared plus 4 squared. The top, you're just going to have to FOIL it out, figure out what you got. You got negative 3 times 5, that'll be negative 15. Minus 12i outer, a plus 10i on the inner product, and then a plus 8i squared. Top. So cleaning that up, we're going to have negative 15, minus 2i, and then minus 8. I squared being negative 1. In the bottom, we just do the arithmetic. It's going to be 25 plus 16. So that's going to add to be 41. And then negative 15 minus 8 would be a negative 23 minus 2i, and then all over 41. And I'm perfectly happy right there. If you want this in, according to Hoyle A plus BI form, you can split this into two terms, negative 23 over 41 minus 2 over 41. All right, but it's still a complex number for sure. Any questions on that? All right, so that's division. Let's do this here. So another thing about this imaginary unit I. If we were to take a more advanced algebra course called abstract algebra, we would find out that the number I and its powers of I form what's called a cyclic group. Now, think cyclic as in cycling. If we make an observation starting with I to the first, that's I. I squared, we already know, is negative 1. Now, I cubed would be, now, and here I'm using exponent rules. Simply, if you multiply two things with the same base, you add the exponents. So I could break up I cubed to be I squared times I to the first, because 2 plus 1 would be 3, which means it's negative 1 times I, so that's negative I. So I cubed is negative I to the fourth, doing the same thing, I could write that as I squared times I squared, which would be negative 1 times negative 1, which is 1. And this is where it now begins to cycle. Because if I continue on and look at I to the fifth, I to the sixth, I to the seventh, I to the eighth, and get these results, I to the fifth I can consider to be I to the fourth times I to the first, which would be 1 times I, or is I. I to the sixth I could break to I to the fourth times I squared, which would be 1 times negative 1, which is negative 1. I to the seventh I could write as I cubed times I to the fourth, which would be negative I times 1, or negative I. I to the eighth I could write as I to the fourth times I to the fourth, 1 times 1. And you see it how it's cycling. And it's actually going to do this forevermore. That is, I give you any power of I. These are kind of ellipses going this way, indicating it's just going to keep repeating this cycle forever. If I said find I to the 343rd power. So not knowing anything else other than what I just showed you, you'd have a 25% chance of being right if you guessed, because you know it's got to be one of those 4. You got a calculator handy there? It doesn't matter. It could be a phone calculator or a graphing calculator, doesn't matter. Just some kind of calculator. All right. So just simply do this. On your calculator, take 343 and divide it by 4. I'll do the same here. So you take 343 and divide by 4. You should have gotten 85.75. All right, all I'm really interested in is the remainder. What is the remainder? When you see 85.75, what number is the remainder of that division? Do you surmise? Okay, so here's the thing about calculators. I don't care what kind of calculator you have. It could be TI-84. It could just be a little tiny solar kind of arithmetic type calculator. When you divide on a calculator and it doesn't go evenly, that decimal part, in this case 0.75, is the decimal form of a fraction. That fraction is the remainder over the divisor. Now remember, our divisor here, we divided by what? 4. So 0.75 is what? 3/4. We divided by 4, so the top part is our remainder. That is, if we divide 343 by 4, it's gonna go 85 times with a remainder of 3. Make sense? So division by 4 is easy. If you get 0.5, your remainder was 2. If you get 0.25, your remainder was 1. If you don't get a decimal at all, and then it went evenly. And so the deal is simply this, as far as how this works, the remainder was 3. So this simplifies to I, negative I. If you get a remainder of 1, it's I. If you get a remainder of 2, it's negative 1. If you get a remainder of 3, it's negative I. If it goes evenly, it's 1. We know anything to the 0 power is 1. So notice if you go backwards, I to the 0, 1. So it cycles the other way too. Now, if I would write out why this works, that's just how it works. Then this is working because I can use power rules. We divided it by 4. We knew it went 85 times. So I to the 343 would break down to I to the 4th times 85, and then times an I cubed. So you would have 4 times 85, which would be 340, plus that 3 to get back to my 343. But we already know that I to the 4th is what? 1, and 1 to any power is 1. And what are you left with? You're left with I cubed, which is negative I. And so that's why it works. Any questions on that? All right, there are going to be a couple problems in the homework that's going to have you deal with I to a negative power. And 2 ways around that. You could divide into the negative number and get the remainder, divide it by 4. But that can be a little tricky sometimes for folks. So let's say I was looking at I to the negative 23rd power. Now it's still got to be one of these 4. So a couple ways about it. Now I really don't have room here, so we're going to go to the next page. Give myself a little room here. I to the negative 23rd. All right, so if you would divide 4 into here, all right, kind of the trick doing this by hand is to first think, how many times would, if I was just dividing 4 into 23? Well, it would have to go, what, 5 times, right? Okay, so what I'm going to do is I'm going to bump that up 1 to 6, and I'm going to make that negative. That is the quotient. Now, negative 6 times 4 is negative what? 24. And then what do you do in ordinary division? You subtract. Oh, but that's going to give me what? Negative minus a negative. That's double negation. That's going to turn into negative 23 plus 24, which gives me 1. And when you divide by 4, your 4 possible remainders are 0, 1, 2, 3, and that's it. Those are my 4 possible remainders. So your remainder here is 1, which says this has to be what? I the first. All right. So if you don't like that, you can do it this way. Take that I to the negative 23, oops, power, and write that negative exponent as a positive. But remember, that means take the base to the bottom and write the exponent positive. Now you got 1 over I to the 23rd. All right. Now, its conjugate here, in this case, excuse me. Oh, let's see here. Do that. Let's make this. Well, yeah, let's do it this way. So once I get that I to the 23rd, if I divide 4, that is, I want to simplify this I to the 23rd first. So get rid of the multiplication. I'm rewriting it. 4 divides into 23 5 times, remainder of 3. I to the cube, I third was what? Negative I. All right, so this would be this. And then use the division, that is multiply top and bottom by the conjugate would be, which would be I in this case. Now, negative I times I is a negative I squared. I squared is negative 1, and the opposite of negative 1 is 1. So I end up with I over 1, which we arrive back at the same answer, which we should. All right, any questions on that? There'll be a couple that you're going to deal with negative exponents. All right, so one last thing in this section, 1.3, is now taking that to quadratic equations. And let me just go find one real quick. So now we can solve any quadratic. In 1.2, you had a few problems where you just answered no real solution because the radicand in the quadratic formula was negative. We called the discriminant. And now we can go ahead and solve in the complex number system. So let me go find one. All right, this will work. All right, so this is from your homework. This is actually number 29 from 1.3. And it is solve the equation in the complex number system. So you've got x squared minus 8x plus 97 equals 0. So not factorable for sure. So I'm going to shoot straight to the quadratic formula. X equals opposite of negative 8 plus or minus square root of negative 8 squared minus 4 times a, which was 1, times c, which is 97, all over 2a, or 2 times 1. And we simplify. So opposite of negative 8 is 8. Now we got to do the arithmetic here. I want to grab my TI and just calculate what is negative 8 squared minus 4 times 97. And I get negative 324. So definitely going to get complex solutions because we're going to take the square root of a negative there. And the bottom, I've got 2. So what I'm now going to have here is, and simplifying now here, you got 8 plus or minus. It just so happens 324, I believe, is a perfect square. It is the square root of 324 is 18. 18 squared is 324. So I've got also the square root of the negative, which comes out as I. So this is 18I all over 2. All right, now be careful here arithmetically. Don't cancel through terms. All right. If you put this answer in my math lab, it's going to kick back and say correct answer, wrong form. And it's simply because the fraction's not reduced. And if you have multiple terms up here, you have to factor out GCF and then cancel with the bottom. So in this case, I can factor out a 2 out of the top, which would give me 4 plus or minus 9I. And in the bottom, I've got the 2. Now you can cancel these guys. And your final answer is going to be 4 plus or minus 9I. Good. So there's actually in the beginning sections of the questions, there's it's going to ask about this. Anytime you get a complex solution, let's say just hypothetically, I've got a problem and I got 5 minus 4I as a solution, then you're guaranteed 5 plus 4I is also a solution. They always, complex solutions always come in conjugate pairs, right? Okay, so that was kind of the fly by night version of complex numbers, but I have gotten through everything that you're going to be asked about in the homework for those who haven't got to it yet. I'm not going to assign any more homework beyond what I've already assigned with 1.3. So now I put as the due date today, and that was really for pacing. Again, you can work past the due date with no penalty. That means if there's a homework section and there were a couple problems you didn't get at the beginning of the semester, you can go back at the end of the semester and do those homework problems. Clear on that? Okay. And that works for quizzes as well. So speaking of quizzes, that I am going to assign our first quiz, which will cover, and there are a couple linear equations, but you guys should be okay with those, and then quadratic equations, and then this 1.3 material. So remember, on a quiz, they can be taken an unlimited number of times, but you have to take the whole quiz, right? So first time you take it, you get a 8 out of 12. You can't just go back and do the 4 you missed. You have to take the whole quiz again. Same problems, conceptually, different numbers. So I am going to go ahead right now and assign quiz 1. So our next official day to meet will be on Tuesday of next week, and which will be the 25th. So I'm putting the due date of this quiz to be the I'm going to make it the 24th, which would be the day before. So I would like everybody to have taken that quiz at least once, but prior to class on Tuesday of next week. Set that. Set that. All right. It is saved.